Okay, so in this lecture, we're actually going to go over the impulse response. And what we will find out is that when we couple the impulse response with convolution, what we learned in the previous lecture, we will have a very powerful technique to analyze circuits. Before we start, I'm gonna briefly overview what we learned in the last lecture. So in particular, we introduced convolution. So we said that convolution would take two functions, so x of t, two functions in time, and y of t, and we said that it would generate another function by integrating them, and then you stuck tau on the first argument, and then y of t minus tau in the second argument, d tau. So now you get another function in time. So for each instant in time, the value of this integral will be different, and that's what we call the convolution. In this class, we're going to introduce the impulse response, or h of t, which is a very special kind of function. It's a function that actually solves a differential equation. So remember a differential equation of the form a0 x of t plus a1 d dt of x of t plus a2 d dt squared x of t equals a delta function. So in particular, whenever we solve a differential equation of the form, we call the solution h of t. So I'm not even going to write x of t here. I'm going to write h of t, or the impulse response. And in the next few slides, what we will learn is that once we know this, then if I were to try to solve a differential equation of the form a x of t plus a1 d dt of x of t plus a2 d dt squared x of t equals y of t, what we will find out is that our solution to this problem will be that x of t is simply equal to the convolution of the input y of t with the impulse response. So that's why we had to learn convolution, because as it turns out, when we want to analyze when we want to come up with the solution to a general differential equation, we're going to have to use convolution. And in particular, what we convolve with is what's called the impulse response, which is the subject of this lecture. So I'm going to talk about this, but before I do, let's review a little bit from our previous. So just as a reminder, convolution follows the commutative property, the associative property, distributive property, this differentiation integration property, the shifting property, time shifting property. In addition, in the next couple of slides, I'll go over a couple examples of convolution. But all of these properties you can solve for basically convolving any function in a function. Now, in particular, today we're going to be using this to develop a little bit of a theory for analyzing circuits using our impulse response and convolution. Okay, so now we'll just go through a couple of examples. So why don't you pause the video and try doing this particular example. Okay, so now we go over this example, and this particular example involved two unit step functions. So here I show them. And so basically what you can do is from the unit step functions, I hope that going from there to here wasn't a big trouble. So this is the identity for when we convolve with function times a unit step function. So that changes the limit, and we get this unit step function outside. And then finally, we're left with this integrand. And here, since the e to the negative 3t only is only a function of time, we can actually take it out of the integral because the integral is in terms of tau. So we're left with this. And to do this kind of integral, you typically go to a table of integration. So I went and looked this up. And once I went to the table of integration, what I got was that that integral is actually this. And okay, so once I had that, I apply the values for the limits of the integration. And after you evaluate it and you clean up some terms, you end up with something that looks like this. So it's the convolution can get, and I wanted to show this example, which is a more some example, just to show you that the convolution is as hard as what it is to evaluate these particular integrals. Once you know how to get the correct limits, the rest it's pretty much how much Calc 2 you know, or how good are you at computing antiderivatives. All right, so let's look at one more example. So here we have the convolution with the delta function. So why don't you go and try and do this? So pause the video and do it. And so for this particular one, all you had to do was realize the time shifting property. And you realize that when you convolve with a delta function that's time shifted, you just get whatever you put in back time shifted. And so that is your output function. Okay, I said I would stop early today, so that's all I have for today. Thank you very much. Hope you have a good rest of your day. Okay, so let's say in this particular case, I want to solve this particular differential equation with forcing function y of t. So y of t could be anything. It could be e to the negative t sine t plus cosine t plus t cubed minus 7, whatever. So let's say I want to solve this equation, and I know that this particular same differential equation, when I have a forcing function of a delta function, my solution is h of t, or what we call the impulse response. So what I'm going to actually claim is that the solution is actually simply the forcing function that I just drew here, that's very complicated, convolved with the impulse response. So first, for x, in the first expression, I'm gonna replace y sub t convolved with h of t, and then I'm gonna again replace y sub t convolved with h of t, and then again replace y sub t convolved with h of t. So let me write out all these convolutions. So I have a0, the integral, and then this should of course be equal to y sub t, which is also equal to a0 times y sub tau h of t minus tau d tau, and then negative infinity to infinity, plus a1, the derivative ddt of the negative infinity to infinity of y sub tau h of t minus tau d tau, and then I'm going to have another one, a2 d dt squared, the integral from negative infinity to infinity of y sub tau h of t minus tau d tau. Now, notice something in particular, which is that these derivatives are all with respect to t, so I can move the derivative here, and I can move the second order derivative here, and to these three integrals, the y sub tau is common, and so I can actually combine the three integrals, so I'm just going to do that. So I'm going to have y sub tau, and then I'm going to have a0 h of t minus tau plus a1 d dt h of t minus tau plus a2 d dt squared h of t minus tau d tau. Well, look, by definition, this is actually just the delta function. So I'm going to get that this is actually the integral of y sub tau, deltas of t minus tau d tau. which is actually just equal to y sub t convolved with delta sub t, which is equal to y sub t. So as you can see, this is actually the solution to this differential equation, because when I plugged it into the differential equation, I got y sub t. So indeed, this works. So as you can see, if I can find if I can find a solution h of t that solves for a forcing for a input function deltas of t, then that would mean that I can just keep using that solution to find the solution due to any input. So that's what's so special about this so-called impulse response. Okay, so here's the derivation more cleanly. So I have the the differential equation I want to solve, and then I assume that this was my solution. And then here I go through all the same steps I went through in the previous slide to show you that indeed this is the correct solution to this differential equation. Okay, so in particular, that's basically what today's lecture is all about, the impulse response. We're actually gonna talk about how to find the impulse response for a circuit. And then we're also going to, and this is basically why we want to find that impulse response, because then we can use this property. Okay, so in particular, what we're actually looking into is what we call linear system theory, which just basically says if I have an input or a forcing function x of t, and it goes through a linear network which has an impulse response h of t, the output y of t is actually just x of t convolved with h of t. That's basically what linear system theory says. Believe it or not, all of you have already been doing convolutions, but instead of in time, you've been doing them in space in your physics classes. So if you remember when you were in your physics classes, if you wanted to find, if I have a charge Q, and I wanted to find the amount of voltage due to that charge, I would usually have to do kind of the 1 over the distance. Now, if I had a distribution of these charges, I would have to do an integral of 1 over the distance times the q's of r prime, dr prime, r minus r prime, where r is my observation variable and r prime is the charge location or source location. This is actually a three-dimensional convolution if you look at it, because you're really convolving 1 over the distance with the charge. So if I think of this kind of, if I were to write this 3D convolution, it would be kind of the integral from negative infinity to infinity. All the x, y, and z become x prime, y prime, z prime. And then dx becomes x minus x prime, y minus y prime, z minus z prime. If this notation makes you uncomfortable, think of this as a tau x, tau y, tau z, tau y, tau z. And as you can see, you're just doing a three-dimensional convolution of the charge with the electric field. As it turns out that 1 over the distance is actually the what we call the Green's function for the Laplace operator. So if you have Laplace of h of t of r, sorry, of location equals deltas of r, the solution is actually h of r is equal to 1 over r. So that's basically applying the same logic, but instead of in the time domain, you've been applying it in the space domain. Well, now we're going to apply it in the time domain to solve circuits. Okay, so how do we determine the impulse response? There's actually a very simple heuristic given in the book. which uses the fact that the derivative of the unit step function is the delta function. And so what we're going to actually do is take the circuit, start with our differential equation, assume that the input is a unit step. Once we assume that the input is a unit step, we're going to come up with what we call the step response. So the step response is just the input when the solution when the input is a unit step function. And then we're going to just take the derivative of the step response, and that's actually going to be our impulse response. Why? Because if I take this equation here and I apply a derivative with respect to time, on the left-hand side, I'm going to get a delta function. On the right-hand side, I'm going to get the solution dx of u of t, which is actually the impulse response. So it turns out that I can just simply solve the step response, take its derivative, take the derivative of the solution, and that's going to give me the impulse response. Okay, so that's basically all you need to know how to do in this class. I'm going to go over a few examples and go over this in a little bit more detail in the next slides. Okay, so first I'm going to show you that this does indeed work in a more rigorous way. It's kind of what I just showed you in the previous slide, but much more cleanly. So in particular, if we look at here, we start with our differential equation, but with use of t as our forcing function. Okay, use of t as our forcing function, and my pen decided not to work. Okay, so we have use of t as our forcing function. Now what I'm going to do is I'm going to take the derivative of both sides of this equation. So I'm going to get here the derivative of the unit step function, which we defined in the previous lecture as the delta function. And then we will also get here the first derivative. This will become a second derivative, and this will become a third order derivative. I can factor out one derivative from each term so that I have basically in parentheses one of the derivatives. And if I call this h of t, the thing in the parentheses, then I get back my differential equation with a delta function on the left-hand side. And so indeed, the derivative of the unit step response is the impulse response. So that's what we're going to use to basically analyze to determine our impulse responses. So the general procedure we're going to be using for solving circuits from now on is summarized in this slide. So first, we're going to derive our differential equation for our circuit. And like I said, for the rest of this class, all of the circuits we're interested in are either first or second order, so they're going to be of this form. And then we will assume that our input is a unit step function. Okay, and then once we have our assumption for the input, we're going to solve for this unit step response, and I'm going to go over how to solve this in the next few slides. To be able to solve this, you actually needed to study switch circuits, as we will see. And then once we have this unit step response, we take its derivative, and that's going to give us the impulse response. Once we have the impulse response, we can determine what the output is by simply convolving it with the input forcing function y of t. So basically, first we're going to find the impulse response. Well, actually, that would be steps 2 and 3. And then use convolution to find solution. Okay, so that's what we're going to be doing. I'm going to go over now some examples since I've already gone over the theory for this particular class. Okay, so how do we find the unit step response? So you have to realize that a unit step response or a unit step on a circuit is really the original source, with a 1 DC source and a switch that turns on at time equals 0. This means that all initial conditions will be 0 when we analyze a unit step response, and our forcing function will be a 1 for time greater than 0. So basically, if I want to model this, I have to analyze this circuit. If I want to model this, I have to analyze this circuit. And if I want to model this, I have to analyze this circuit. And the only difference between the circuits on the left and the circuits on the right is that you replace the source with a unit DC source and a switch that flips at time equals 0, connecting that source. That's it. Okay, so let's look at an example. So let's say we wanted to analyze this particular circuit. So first, for time less than 0, we have basically, and then a 1 here, and then a resistor, and then a capacitor, which is 2 ohms, and 1 over 2 farads. Well, in this particular case, we have that nothing has been connected to the circuit, so we know that VCs of 0 is going to be equal to 0. Now let's find the differential equation for this circuit. So basically, now for time greater than 0, we're going to have the same circuit except with the source replaced by 1. So we know that our initial condition will be that VCs of 0 equals 0. And as for the differential equation, I can apply KCL, and I'm going to get that 1, or the input current, is equal to the voltage across the capacitor, and then this is the unit step response, so I'm going to add a U there, divided by 2 ohms plus 1 over 2, the capacitance, times the time derivative of the voltage across the capacitor. And I'm adding a U here just to signify that this is the unit step response. Okay, so that's our differential equation. For time less than 0, we've already said what happens. Basically, we have that VCs of 0 minus equals 0. Okay, so now we need to solve this differential equation with the right-hand side replaced by 1. So first we need to find VC particular. Well, in this particular case, to find VC particular, we're going to assume it's a constant CP because our left-hand side is constant. And so to find CP, we're going to plug it back into the differential equation, and we're going to get that 1 equals CP over 2 plus 1 over 2 ddt of CP. But you know the derivative of a constant is 0, so we're just going to get that this is just CP over 2, which tells us that CP equals 2. So now we know what that constant is. Now we need to find the homogeneous solution. So to find the homogeneous solution, first we have to find the characteristic equation. So for this particular differential equation here, it's going to be 0 equals 1/2 plus 1/2 lambda. So remember, first order derivative becomes lambda, 0th order derivative becomes lambda to the 0, which is just a constant. And yeah, so now we need to find the roots of this equation, and we're going to get that lambda equals -1. And then we match our initial condition, so we're going to have that 0 equals 2 plus C homogeneous e to the -t, and that's going to give us that C homogeneous is going to, or e to the -0. So I guess that's going to give us that C homogeneous equals -2. So our final solution is going to be 2 minus 2 e to the -t is our unit step response. So that's going to be VC's U's of t. Okay, so now that we know our unit step response, we need to figure out what our impulse response is. And in particular, this should be this times u of t. And so to find the impulse response, we just simply need to take the derivative of this. Okay, I got a little bit ahead of myself. So for time less than 0, we have that all quantities are 0. For time greater than 0, we have that this is the answer. So what we're going to do is we're going to multiply our solution by the unit step function to make it 0 for time less than 0 and greater than, and 2 minus 2 e to the negative t for time greater than 0. So this is effectively taking care of the fact that we have a different solution for time less than 0 than the one we have for time greater than 0. Okay, so we found our unit step response. Now what is the impulse response? Well, to find the impulse response, we just simply need to take the derivative of this. So we're going to take the derivative. So we have that d dt of vc of t is actually going to be equal to d dt of 2 minus 2 e to the negative t u of t, which is actually going to be equal to u of t, the derivative of 2 minus 2 e to the negative t, plus 2 minus 2 e to the negative t, the derivative of u of t. So this derivative is pretty easy. So the derivative of 2 is just equal to 0. The derivative of negative 2e to the negative t is just 2e to the negative t. So we're going to get that this is actually going to be equal to e to the negative t times 2 u of t plus, and the derivative of this is a delta function, so we're going to have 2 minus 2 e to the negative t, deltas of t. So here's where I'm going to do something a little bit tricky. So we know that the delta function is 0 for t not equal to 0. So I can just replace this thing in this argument by its value at 0. So I'm just going to basically, because since this is 0 for any time less than 0, I can basically change its value after 0 and it's not going to change anything. So if I evaluate this at 0, I'm going to have 2 minus 2. And so that's going to give me 0. So my final solution is actually just that h of t equals 2 e to the negative t u of t. That's it. So an important property that we will be using is this one, which you should actually memorize, which is that f of t times deltas of t is actually equal to f of 0 deltas of t. And the reason that is because deltas of t is 0 whenever t does not equal 0. And so we can place whatever we want for the function at any time other than 0. As long as we replace this thing here with anything, as long as it matches at 0, the product will always match because the delta function is 0 anywhere that's not 0. Additionally, if I have a time-shifted unit step function, so for example, f of t times deltas of t minus t, then that's going to be equal to f of capital T deltas of t minus capital T. So in this particular case, we found out that when you evaluate this thing at 0, we get 0, so that's why we could remove it from our solution. Okay, now we found the impulse response, so now we can actually solve the circuit for any input if we wanted to. Okay, so yeah, so here I kind of emphasize that I can replace that f of t deltas of t is equal to f of 0 deltas of t. So I use that to plug in 0 for my argument for the 2 minus 2 e to the negative t. Okay, so now let's say that this is the input to my circuit. What is the output? So to find the output, VCs of t, now that this is my input, all I have to do is basically find the convolution of t use of t minus 1 convolved with 2 e to the negative t u of t. And so let me just evaluate that now. So we have basically that this is just then from negative infinity to infinity of tau use of tau minus 1. And then I can factor out the 2 e to the negative t minus tau use of t minus tau d tau. So just remember that when you're doing convolutions, you got to figure out when these things are off. So this one is off when tau minus 1 is less than 0 or when tau is less than 1. And this one is off when t minus tau is less than 0 or tau is greater than t. So that tells me that I can start my integral from 1 and I can end my integral at t. So then this becomes 2 use of t minus 1, the integral from 1 to t. And remember that if this upper limit is smaller than this lower limit, then the whole integral should be 0, because it means that the two are never on simultaneously, and so that's why we multiply by this unit step function t times t minus shifted by 1. Okay, so and now we have tau e to the negative t minus tau and yeah, d tau. At this point, you can just go ahead and go to your computer and basically do this integral, and you found the solution to the circuit. In the next slide, I actually have done it already, so here it is. And to do that, I use this integral identity. So this is where I left up in the previous slide. Then I basically separate out into two exponentials. I factor out one of the exponentials, and then you have to do this integral. Well, that integral is actually described right here. And then once we have the solution to that integral, you end up with the following solution. So that's it. That's the impulse response. Okay, so here I actually took the solution we got on the previous slide, and then I found its derivative. So here's the solution we got in the previous slide. Here it's its derivative. And then I plug in the values into the differential equation, and I indeed get back the solution to the differential equation. So you can see that this actually does work out. All right, so far mathematically, I've kind of given you an idea of what this thing looks like. And I've told you kind of a recipe of applying these convolutions to the impulse response. But philosophically, what are we really doing? So now I'm actually going to try to unpack it a little bit. So let's for now assume that our impulse response is actually this one here. So it's different from the one in the previous example. And we know that the output is going to be V out convolved with V in. So it's going to be V in convolved with the impulse response. So here I actually plot the impulse response, and then I plot the input. So at time equals 0, what I have to do is I'm going to flip the impulse response, so h of t minus tau. So I'm going to flip the impulse response. And to get the response at time equals 0, remember, I'm going to take the product of this times my input. So I'm going to do this at various time steps, and I hope that you can get an idea of what we're actually doing. So at time equals 0, here's kind of our two functions in the tau plane. We have here h of t minus tau, and then for t I've plugged in 0, and then what vn is. And what we're going to get is that when we take the product of the orange line with the blue line, we're going to get 0 everywhere. So when we take that integral, what we're going to get is actually 0. Actually, for all time less than 0, we're just going to get 0 because our input's not on. That's not that interesting. So then we go now to time equals 1. So now we're evaluating at time equals 1. We'll now look at something magical. The input at time equals 1 gets weighed with the amount of the impulse response at 0. And then the thing that happened a little bit before gets weighed with a little bit more weight, less weight, and then the thing that gets happened a little bit before gets multiplied by a smaller and smaller number. And the thing that happened very long ago gets weighed very little. In this particular case, we still have 0. Okay, so now let's look at time equals 2. So this is a little bit more interesting. So when we look at the product of the orange line and the blue line, it's going to be something that looks like this. I'm going to draw it up here. So I'm going to have basically now remember my output at this time step, at this time location, sorry, is actually what's under this curve. But what is the physical meaning of what is under this curve? Well, I took the input at the present and I multiplied it by the amount of the impulse response at 0. Then I took the input a little bit in the past, and then I multiplied it by the impulse response a little bit behind. And then I kept doing this for the whole history of inputs to create this waveform. And then this waveform that I created here, my output is actually the area of this waveform that actually has a weight version of the history of inputs. So now I got my number. Well, if I now want to find the solution a little bit later, so let's say at this time location, I'm going to take the product again of the orange line with the blue line, so I'm going to get something that looks like this. And then it's going to be 0. And again, I'm taking the present input and I'm multiplying it by the kind of the highest value for the impulse response. Then the little bit delayed, I'm also multiplying it again by the amount of the little bit delayed, and so on until I get this waveform here. And the area under the curve of this waveform, which actually is kind of a weight history of the inputs, is actually my output. So one way to think of this impulse response is as a recipe that combines all past inputs as a prediction for the present output. Now, you could also you can attach different meanings to this thing. So, for example, you could think of this as the y-axis as the state of your friendship with a friend, state of friendship. And then your input could be kind of negative if you got in a fight with your friend, positive if you didn't get in a fight, if you had a good interaction with your friend. Now, what you would expect if you want to see the state of your friendship at any given type of at any given time, what you would want to do, you would weigh your recent interactions more than your more four-way interactions. So basically, if you got in a fight with your friend months ago, at this point, it's not going to really affect how you feel about your friend currently. But if you recently got in a fight with them, then it's going to affect how you feel about them at the current time. And so the recipe that you would kind of do to figure out the state of the way you feel about your friend would be that impulse response. Okay, so I can keep moving this response, which again gives me a way to weigh the current input and past inputs in order to predict the current response of the circuit. So this somehow encodes the system so that I already know how to look at the time history of inputs to predict the output. So I can keep going, going, and going, and eventually I get my solution. So I hope this gives you a more intuitive way of why this convolution and why this impulse response works, and what the concept behind it is. Effectively, the H of T is a template that tells you how to use the present and past inputs in order to predict the current output of the circuit. Yeah, so that's basically the impulse response. I'm not going to go over the next few examples, but I have some extra slides, so you should probably try to solve those on your own. So particularly follow all of these steps. The solutions are actually posted, so you should be able to go through it on your own. It's the same idea. You first derive a differential equation. You solve the unit response. You take the derivative of the unit response to get your impulse response, and then you do the convolution with the input in order to get the output. And then here I have another, you could also do this one, but that's quite lengthy. I never actually tried doing it. It's just to give you an example. And then you could also try this one, which is another first order circuit. And here's the solution to that. Okay, so I guess I'll see you on Tuesday.